Hi, I'm Ono and I'm presenting Commit to the Bit, Reactive Reinforcement Learning Done Right. This is joint work with Claire Bernard and Michael Mühlebach. In reinforcement learning, we consider the setting where an agent interacts with an environment. So the environment has an internal state, X, and it sends an observation to the agent. And the agent has an internal state, Z, and it responds with an action, U, to the environment. And we assume that this cycle ends after some number of steps. So this is an episodic reinforcement learning setting. And we also assume that all these sets are finite. So in reinforcement learning, the goal is to learn this agent function so as to maximize the expected sum of rewards over the course of an episode. Okay, and in this work, we also assume that the agent state Z is equal to the current observation Y. So this means that this is a reactive agent, and this observation Y is equal to some function phi of the environment state. So in this case, this is a deterministic observation function, or it's also called a hard state aggregation. Now, why do we study this setting? So reinforcement learning has seen a lot of progress in the past 10 to 15 years, specifically when applied to large and partially observable environments. And in this setting, the agent has to act with incomplete state information. So this makes it a non-Markovian reinforcement learning setting. And even though this often works in practice, the theory that we have cannot really explain these empirical successes that we have seen. So before going to the non-Markovian reinforcement learning setting, I want to go back to the basics and see where does the theory, where do the algorithms that we have break down in this setting. So what I'm showing here is a very simple environment. They're called a corridor environment. So an episode starts in this state here, and then you can either go to the left and terminate immediately with a reward of -1, or you can go all the way along this corridor and get a reward of -1 at every time step until you get a reward of +k at the end. There's k of these intermediate corridor states, so this adds up to a total return of 0. Right? So the optimal policy in this case is to go to the right. Now, how can we find this optimal policy algorithmically? Well, one way to do this is to first solve for the optimal value function. So the optimal value function is defined as the maximum possible achievable expected reward when starting in a given state. And if we have this optimal value function, then we can find the optimal policy using a one-step look ahead. So for example, if we're in this state and we want to know should we go left or right, then we can just say, okay, if we go to the left, then we get a reward of -1 and an optimal value of 0, so that adds to -1. And if we go to the right, then we get a reward of -1 and a value of 1. So that adds to 0, and that's better. So we go to the right. So how do we get the optimal value function? Well, it satisfies this Bellman equation. So we can write it as B star is equal to B star of V star. And B star, the Bellman operator, is a contraction mapping. So value iteration basically solves the Bellman equation by fixed point iterating this Bellman operator. Okay. Now, how can we do this in the reinforcement learning setting? The problem here is that we cannot evaluate this expected value, right? Because we don't have access to the environment dynamics. So instead, we can replace it by samples. And a second problem that we have is that even if we have this optimal value function, we can't do this one-step look ahead, right? Because again, we don't have access to the dynamics. So instead, we can shift from learning state values to learning state action values instead. And of course, if we do these two things, then this algorithm is called Q-learning. So we start with an empty Q table. Then we sample our first state. We sample an action from a behavior policy that we assume is fixed for the whole duration of the algorithm. Then we get our new state, and we update our Q values. We go a small step into the direction of this sampled Bellman operator estimate. And then we either start a new episode if we reach a terminal state, or we go to the next state. Okay? So it's a very simple algorithm, and we can show that it converges almost surely to the optimum policy if the environment is fully observable and tabular. Okay. Now, the problem is that only boring environments are tabular and fully observable. So let's go back to the non-Markovian setting. And for example, let's consider this simple corridor environment where all these corridor states that really are, in a way, representing the same thing, they are all aggregated together into a single state. So the agent cannot distinguish between them. It only sees the same feature z equals 1 for all of them. Okay. So now the big question is, can we still do value-based reinforcement learning in this setting? And if so, what is the meaning of values in this case? Okay. So the first thing we can try is we can just use Q-learning in this modified corridor environment, and we just, instead of learning state action values, we learn feature action values. But it turns out that this approach fails. So we see here, I'm plotting here the performance of the greedy policy over time. And we see that this fails. And this failure actually agrees with the theory. So Q-learning is in fact only guaranteed to converge to the optimal policy if the environment is Q-star realizable. So Q-star realizable means that if two states share the same feature, then they need to have also the same values, the same optimal values. And in the corridor, we saw that that is not the case, right? And in a way, this observation also makes sense, right? So if we have a feature like this where the value is different in all these states, then how can we hope to assign a single value to all of them and still assume that this works, right? So to understand when we can maybe do this, let's think back to how dynamic programming works and what do we actually need our value function to do, right? The first and most important point is that the point of the value function is to guide behavior, right? So if we have a value function and we take a one-step look ahead of this value function, and then we take the greedy policy, then this should improve our policy, right? And the second point is that, of course, we need to compute the value function somehow. So, for example, if we want to use a Q-learning type algorithm, then this value function should be computable by some kind of contraction mapping, okay? So this is what we would like. So let's first start maybe with a fixed policy and see if we can understand what the value function, the feature value function of this policy should look like. So here we have the policy that always goes to the right. And to now come up with a feature value function that corresponds to this policy, we can just open a book on reinforcement learning and we will see that this question has been studied before, right? So for example, we could minimize the mean squared value error. So I've written down the definition here. And then we get a value function, a feature value function that looks something like this, okay? So it assigns this number to all states in the feature. Or we could minimize the mean squared Bellman error, so a very similar definition, and we get a different kind of solution. And at first glance, both of these proposals look reasonable, right? Because, for example, if we start here in the first state and we do a one-step look ahead, in both of these cases, if we go to the right, the value of this state is larger than the value of the state on the left. So that means if we take a greedy approach, then we're going to go to the right, which is the correct behavior in this case. But this already breaks down if we change the environment very slightly. So if I replace this reward with -1 here with a +1, then, well, now if I do a one-step look ahead, this value on the right can still be greater than the value on the right here can still be greater than the value of going to the left, right? Because if k is large, then this one here, even if we subtract 1, is going to be greater than +1. So even in this very, very simple corridor environment, this approach breaks down. So let's try to do something a little different. And in particular, let's try to just put ourselves into the shoes of this agent walking around in this environment, okay? And let's first also assume that this agent maybe isn't too bright. So it doesn't understand that this is a non-Markovian environment, right? So in particular, let's say that the policy again is equal to the one that always goes to the right. And now if the agent is in a corridor state, so it sees that the current feature is 1, then sometimes it sees that the next feature is also 1, and sometimes it sees that the next feature is 2, right? Now our agent that is not so bright says, okay, I sometimes see different things. So that must mean that I'm in a stochastic MDP, right? So we know that that's not true, but the agent thinks this. And the agent can even write down the probabilities, right? So under this policy, the probability of seeing another feature 1 when I am in the feature 1, I see this k minus 1 out of k times, right? So that corresponds to all of these states. And then for the last state, here I see the feature 2, right? So then also the probability of seeing a feature 2 after being in the feature 1, well, I see this 1 out of k times, right? And now if this is nothing but a stochastic MDP, then it's very easy to write down the value function, right? Because we know how to define value functions for stochastic MDPs, right? So if I just write this down here, so we would say that, okay, the value of the state 0 should be equal to minus 1 plus the value of the state 1, right? This is just a Bellman backup for going from here to here. And then the value of the feature 1, now, well, k minus 1 out of k steps, I'm transitioning back to the same feature. So I get minus 1 plus v of 1. And 1 out of k times, I transition to this goal state here, where I get a reward of plus k, and I assign a value of 0 because it's the terminal state. Okay, so I see k, right? So if I solve this, which is very easy, I will just see that v of 1 should be equal to 1. And then we see that this one here should be equal to 0. Okay, so using this very naive approach, we can also get a value function estimate. Okay, so I've written it down here again. So these are the values that this approach gives us. And what's interesting about this is that we got the value of the entrance state. So the value that is assigned to the corridor is exactly the value of this entrance state of the corridor. And this is interesting because this one will always give us the correct behavior, because it's exactly the value we would use in the case where there is no partial observability, right? So here, no matter what we change this reward to, we will always get the correct behavior. Okay, and we can also formalize this approach to say that we are actually minimizing a risk measure that we call the Bellman risk. So this definition, it looks very similar to the mean square Bellman error, but it's a little bit different. And now the big question is, when does this approach work, and how can we adapt it to the reinforcement learning setting? So let's start with the first question. When does this work? Well, first, to have an entrance value, a feature kind of must always be entered in the same way, right? If there's two different ways to enter a feature, then there is no fixed single entrance value that makes sense to assign to a feature. And we can define this more formally in the following way. So an environment is called quasi-Markov if each feature is associated with a fixed, unique entrance distribution sigma, such that whenever we enter into this feature from another feature, so if we are at x and we go to x prime, and these two do not belong to the same feature, then we need that the next state, x prime, is distributed according to this entrance distribution. So for example, the corridor environment is quasi-Markov because if we enter into the corridor feature, we will always enter into the leftmost state of the corridor, right? So this is quasi-Markov. And why do we call it quasi-Markov? It's because in this case, whenever the feature changes, those transitions are Markovian. Because when we enter into a new feature, then the distribution of the state looks exactly like this. And this sigma is fixed. It doesn't depend on any past history. So whenever the feature changes, we can forget about the whole past history of observations. Okay. So in quasi-Markov environments, we can always define an aggregate MDP, M hat, in the following way. So this is an MDP on the feature space. So the way this works is if we are currently in a feature and we have a given action, then we first disaggregate this feature. So we take the posterior distribution over states inside of this feature under the assumption that we have played the same action over and over again since we entered this state. And in quasi-Markov environments, this posterior distribution will always exist. Then we take this disaggregated state and we do a one-step transition. And finally, we take the resulting state and we aggregate again using our feature mapping phi. Okay, and this aggregate MDP, this transition kernel, is exactly what we just had is exactly this stochastic MDP that we just saw in the corridor environment. So what about the values? Well, we can show the following. If we have a quasi-Markov environment and a policy pi, and if v pi and v hat pi are the value functions of this policy in M, so this means it's a state value function, and in M hat, so this is the feature value function in the aggregate MDP, then these two value functions are related in the following way, namely the aggregate feature value of a given feature is exactly equal to the average state value under the entrance distribution of this feature. So this is exactly what we saw in the corridor, right? So the value that we get is exactly the value of the entrance state in the environment. And now a simple corollary of this result is that if we can find the optimal policy in this aggregate MDP M hat, then that policy is an optimal reactive policy in the quasi-Markov environment. So how do we adapt this to the reinforcement learning setting? Well, it turns out that we only have to do a slight, tiny change to the Q-learning algorithm. So I've highlighted it here. So this is at the very end of one step in the environment. So normally at the end, we would sample a new action, and then we're going to apply this action in the next time step. But here in the committed Q-learning algorithm, we only sample a new action if the feature changed. So that means that whenever the feature changes, we sample a new action, and then we commit to this action until the feature changes again. So we're going to play the same action over and over again until the feature changes. And under this change, we can show that this algorithm learned exactly the correct entrance values that we want. And in fact, we can show that it converges to the optimal reactive policy in partially observable environments under a strictly weaker assumption than the Q-star realizability that we have seen before. So first, what does it look like in the corridor environment? So here I'm plotting the results of the committed Q-learning. So for example, if the corridor is 200 steps long, then we see that after about 200 time steps, the committed Q-learning very quickly converges to the optimal policy. Okay, so here is our main result. So what this says is that committed Q-learning converges under standard assumptions almost surely to an optimal reactive policy in the environment if this environment is rewire robust. And rewire robustness is a condition that generalizes both Q-star realizability and quasi-Markov environment. So what does rewire robust mean? So consider this environment shown here. So an episode starts down here on the bottom left, and the optimal policy in this case is to go along this bottom row to get first a -1 reward and then a +1 reward and then terminate. And there are also some other states here, right? So this environment is not Q-star realizable because these three states, they have different distances from the goal, so they have different optimal values. And this is also not quasi-Markov because this feature can be entered in two different ways, right? And either here or here. However, we can rewire this environment, okay? So rewiring in this case means taking these different ways to enter, so in this case these two entrances, and combining them or mixing them around. So for example, we could just switch them. So this would be a rewiring of the original environment, or we can combine them like this. So this is an environment where with 10% probability from both of these actions we go to this state, and with 90% probability from both actions we go to this state. This is actually a quasi-Markov rewiring, because now there's only a single entrance distribution that applies to all possible entrances. And we say that an environment is rewire robust if the optimal policy is preserved from a rewiring like this. So in this case, this environment is rewire robust. We can see this, that in all these cases, in both of these environments, the optimal policy is still to go down here, right? Okay, so I will very quickly go over the argument of our proof. So in the Q-learning algorithm, we have a behavior policy, right? So for example, up here in this environment, the behavior policy says to go up with probability delta and to go to the right with probability 1 minus delta. So that means that here, if we enter this feature here, most of the time we're going to enter on the bottom here, and we are not going to enter on the top so much. And in other words, that means that we can kind of define an average entrance into this feature with higher mass down here than up here, okay? And we can use this average entrance distribution to define a quasi-Markov rewiring of the original environment, in which we just replace all of these different ways to enter into the feature by this fixed average entrance distribution, okay? And of course, for each quasi-Markov environment, we can also define an aggregate MDP, so that same holds here, right? So for this environment, we can also define an aggregate MDP. So why would we do this? Well, the idea is that because this is kind of the average way that this feature is entered, in the Q-learning algorithm, in the long run, on average, it maybe doesn't matter if we're really in this environment or in this environment, because either way, on average, the updates to the Q function might look the same, right? So that's the idea. And in fact, we can prove this by saying that the Markov chain of the state, the action and the next state in the committed Q-learning algorithm admits a stationary distribution mu. And this stationary distribution mu has a specific property, which is that the conditional distribution over the next feature, given the current feature and current action, is exactly equal to the transition kernel of this aggregate MDP, okay? And furthermore, we can show that the algorithm converges to a function Q star that satisfies this equation. And now if we see that this mu down here is equal to the transition kernel of this aggregate MDP, that means that this function, this equation, is the Bellman equation of the aggregate MDP. And so that means that if we take the greedy policy with respect to this Q function, we have the optimal policy in this aggregate MDP, okay? And now by the entrance value lemma that I showed before, that means that this policy is optimal in this quasi-Markov rewiring of our original environment. And so if our environment is rewire robust, that means that this policy must also be an optimal reactive policy in the original environment. So that's the argument. And now to summarize what we've done here, we've analyzed the question, when is value-based non-Markovian reinforcement learning possible? And so Michael Littman showed in 1994 that in general, this problem is NP hard if you don't make any further assumptions. So most existing results require Q-star realizability, but we have shown here that in fact a weaker assumption, rewire robustness, is sufficient. And along the way we have discovered some useful concepts, namely the Bellman risk and quasi-Markov environments. And that's it. Now I want to say thank you very much for your attention, and if you have any questions, don't hesitate to reach out under this link and I'll be happy to answer them. Thank you.